So this is a continuation on the 6.3 video. In the previous video, what we were talking about were vectors and how they have a certain quantity or magnitude and direction. And we learned the component form of these vectors that you can find at any location on a coordinate grid. We can find the horizontal and then the vertical components, such as what you can kind of see in my screen up here. So now we're going to continue on with this, and we're going to look at other notations besides just this component form that you guys started working with. So one special type of notation is called our unit vector form, and what it uses is it uses an I to represent a bold little lowercase I to represent the unit vector 1, 0. So a vector with just a horizontal component of 1, because there's my 1 in the horizontal direction. So then over here we also have a j vector, and that's going to be our unit vector that's vertical. So we're going to be looking at a vector that's just a length of 1 in the upwards direction. Okay, so these are just ones. So that's what this unit vector is and what this unit vector is, not to be confused with imaginary numbers. We're going to start working with these. Number 25 is a lot like what you guys had before. They give us that u is equal to 2I, and they give us that v is equal to just j. Okay, so they ask you in part A to go ahead and take u plus v. The idea is we have operations, and I'm going to scroll up to just show them real quick. We have vector operations that work with component form. So what we're going to want to do is take these unit vectors and get them back into component form. So I'm going to look at u, and what they gave us as u, which is 2I, and I'm going to actually rewrite it as u is equal to 2 times, and then I, which is the unit horizontal vector. So u is actually, now we can take that scale factor, or that scalar multiple, and we can just multiply it in using one of the operations that we were accustomed to in the other video. Alright, v is equal to the j, or just 1j, so j is simply just 0, 1. There's no scalar multiple on this, so it's just 0, 1. So now if we're going to be doing the operations, well, we can just go ahead and take these new component forms that we came up with given the unit vector form, and we can take these component forms and add them up. So now if you were to sketch this, again, what we do is tail to butt or head to butt. Take one vector and we're going to go over 2 up 0. So that's my u. And we're going to add the v right onto that. And so that's just going to be the unit vector of 1. So up 1. So then our resultant is going to be this guy right here. It's the overall movement. When you add up those vectors, what was the just overall movement? How could you have gotten there the quickest? So here was the u plus v, and this actually equals my resultant, so I'll just call it r. And what we would get is, well, you can see, over 2 up 1. So it's going to be 2 plus the 0, because we would add up our x values, but then 0 plus 1, because we added up our y values. Okay, and you can see, yes, that was 2, 1. Alright, part B asks us to do the u minus the v. So if we were to use our component forms that we just got, well, u was equal to, we calculated 2, 0. And then I'm going to change this to plus a negative 1. So we have plus negative 1 times that 0, 1, which we calculated was our v, knowing that j is just a unit vector that's vertical. So here we're going to go ahead and get 2, 0 plus, and then 0, negative 1, because I multiplied that negativity throughout that vector. And what you'll see here is if we sketch it, we would go over 2, okay, and then down the direction of 1 unit. So overall, you can see here what's happening again is we have 2 plus 0, which is going to get us 2, 0 plus negative 1, which is going to get us negative 1, and yes, that overall vector was just a horizontal movement of 2 and then a vertical movement of negative 1. Okay, finally I am going to do C here, and C was asking for 2u, and then instead of saying minus 3v, I'm going to say plus negative 3v. So I'm going to take 2 times my u, which was 2 comma 0. They gave us u originally here. We calculated 2i in component form. So that's what we got. So 2 times the 2 comma 0, alright, plus negative 3 times the 0 comma 1 that v was equal to. So we're going to get 4 comma 0 plus, and then that negative 3 is going to distribute in that scalar multiple, so 0 comma negative 3. If you were to sketch this one, what we're going to be getting is over 1, 2, 3, 4. That's my piece right here. And then down 1, 2, 3. So here we're going to get 4 comma negative 3. So one thing that I want you to start realizing is we've done this stuff before. We have right triangles forming when we're looking at these component forms of these vectors or vector operations that we're creating. What we're getting are resultant vectors from these operations, and these resultant vectors have an overall horizontal component, a vertical component, and a hypotenuse, just like we've been dealing with. So we've been working with component form all this while and getting direction and then magnitudes. So now what if they gave us the other way? What if they gave us just one singular vector with a direction and a magnitude? Could we get these components? So we're going to be looking at something like this. This skill is finding the component form given an angle and a magnitude. So use vector operations or maybe do sketches to help you determine the component forms of the following. I'm going to do number 47 and I'm going to do 53 with you. So number 47 gives us this. Sorry, this is not there. Number 47 gives us this, and what we're trying to do is we're going to be trying to get the component form of this. So let's go ahead and distribute this like we're used to. So we have v is equal to 3 times cosine of 60 degrees times I plus 3 times sine of 60 degrees times j. So now cosine of 60 is just a number. If you look at cosine of 60 on our grid, here's my 60 degrees, right, on that unit circle, and cosine of it is just 1/2. So we're going to take 3 over 2, because I took 3 times 1/2, I, plus, and then we have 3 times, and then sine of 60 degrees. Sine is going to be that y value, so that's square root of 3 over 2. So I'm going to have 3 times the square root of 3 over 2, okay, because that's what 3 times sine of 60 is, times j. So when you get this, what we're going to eventually be able to do is use that definition of I, which is just that unit vector that's horizontal, plus, and then my unit vector, which is vertical, that's my j, 0, 1, and what we're going to get is 3 over 2, 0, plus 0, 3 times the square root of 3 over 2, because all I did was I took that scalar multiple and I brought that in, and so therefore my overall vector is going to be 3 over 2, 3 square roots 3 over 2. There that is. Alright, so we used vector operations. I'm not going to do sketches because we don't have the prettiest of numbers here, but we just determined the component form. Alright, so these are using angles and some old trig to get back into component form. Alright, I have another one. I'm going to have to fit it onto the other page. Hopefully you have more room than I do. But number 53. 53 gives us this double bar line of a vector v is equal to, and then 7/2. Okay, they also give us that we have an angle that's equal to 150 degrees. And they ask for find the component form of v, given the magnitude and the direction. Here's my magnitude, okay, and again that's notation that if you look up here, we did have that definition underneath calculations, so we have magnitude and notation. You'll see those double bar lines. Okay, all that means is we're trying to find the length. So in other words, they gave you the length though. So we know that our vector has a length, vector v has length of, I'm going to write this as a decimal, just 3.5. Okay, so that's the length of that vector. Alright, we also know that this is the direction, so maybe we need to sketch this, so let's do that. We're going to sketch this angle 150 degrees, which is past our 90, so it's 30 degrees off from our 180 degrees. So here right there is my theta equals 150. So here is my vector. And what I need to do is I need to calculate the component form. So in other words, the horizontal and the vertical movement that got me to this point. So here I know that this is 3.5 as my hypotenuse. What you're going to be doing is our old trig rules of, well, what is this length right here? So what you will find yourself doing is cosine of this 150 degrees, okay, comma, and then sine of that 150 degrees, okay, and what we're going to do is we're going to take that times 3.5. Okay, because this length right here is our x value, and what we had is that angle 150. So if you did type in cosine of 150 on your calculator, what you will get is that negative square root of 3 over 2. And you shouldn't be surprised, because we are using that reference angle of 30 degrees, and there's our 30, 60, 90, and it's in the negative direction. Okay, so in standard form, 150 opening from our x-axis, what we have is negative square root of 3 over 2 for that longer leg. Okay, and then the sine of 150 is still using that reference angle of 30, and that's that shorter leg, so that's just 1/2. Okay, so now if you go ahead and take 3.5, actually, I'm sorry, this is better to use 7 over 2 at that point. So this is going to be 7 and then negative square roots 3 over 4, comma 7 over 4, which is approximately negative 3.03, comma 1.75. So that right there is saying you would have to go back negative 3.03 and up 1.75 to get to that point that's going to have the length of 3.5 length with an angle of 30, or in other words 150 degrees, opening from standard form. Now at this point you can finish this. In class today we said draw a line here. That's what the first video will get you, and then tomorrow we'll be working on this in class.